These cell phones, tablets. Make sure that the only thing you have here is your pen and paper. Okay, so all right, so vectors in R2 on the plane, two-dimensional vectors. But I want to make a point here. So what I mentioned last time is that vectors are here, as far as we're concerned, vectors are or will be velocities. They will. Okay, even though what about forces? Forces seems to be a good idea to a way to understand force vectors is forces, because especially with the algebra. Okay, so certainly vector as describing velocity is very appropriate because it gives you the direction and the how fast you're moving. In other words, the speed. Okay, so velocity is surely appropriate, that's fine, but the something that is so your velocity is direction and speed. Okay, so but forces are very nice because the algebra is quite easy to understand. It is literally two different people maybe pulling the object in different directions, and then the end result is a pull in the third direction, right? So then we're going to do that, and then the forces make perfect sense to as analogy as something to be modeled by vectors. And so why do we not think of forces as much? Because forces are accelerations, and accelerations are derivative of the velocity derivative of velocity, which is the second derivative of the position. Okay, so and once again, we have done no second derivatives yet. And no second derivatives in differential equations. So it takes some extra work to make that happen. Nonetheless, there are certain exceptions. I want to quickly take a look at one, and that is a model. Let's say. So first of all, remember the model is that we have had is no forces. What's the effect of having no forces? What kind of motion is that? No forces meaning zero forces. That's mathematical language.
Constant velocity.
Constant velocity, right? Constant velocity, which is a vector, right? So it doesn't have to be a number anymore. So it is literally a vector, and then you kind of once you have it, right? So you go like this. That's a vector, and then you just proceed like this. Constant velocity. So for the same unit of time, you progress forward, and the same amount. That amount is a vector, and that's your motion. We looked into that. Now, I suppose there is one, and then constant velocity, and then by the way, if there's an extra step that we can make, and that is actually position. How would you describe the position? Velocity is constant.
Linear.
Linear. That's right. Linear position. Okay, so so the language, by the way, is entirely one-dimensional. So you have a linear function, the derivative of which is constant, the derivative of which is zero. Okay, so if you go backwards, and then everything stays with us. So except now these are vectors, and so zero linear depends on the position will produce constant velocity, constant vector of velocity, and then zero forces. Okay, no forces, zero forces. Here. Okay, so now I want to throw in extra force, but not as we have done before, say gravity. Okay, the gravity unfortunately is not air resistance. Anybody knows how air resistance appear? What is it? How would we model it? Any idea? Air resistance depends on what?
Okay.
Yes. Okay. So suppose let's just say it's the same shape.
Speed.
It depends on the speed, or technically, so first of all, air resistance is a force. Begin with. So then it will be, well, we'll get into that. And if you write a model here, we would say is, it depends on, naturally depends on the velocity, but we could, depend on speed. Okay, so I can say I like it, to say the speed because it's not enough in the two-dimensional case, or even one-dimensional case, direction matters, right? So you're going this way or that way. So the force, which way it's pointing? Well, in the opposite direction. So it actually depends on the velocity and in a very specific way, right? So that force is, so velocity is v, air resistance is F. What's the relation? How would you write it? Once again, it doesn't have to be two-dimensional. You can think of these as numbers. Possibly numbers. So depends on speed. The simplest model always the simplest dependence is linear. Okay, so that's why we have calculus. Right, so linearization, remember, replacing curve with what? Not with a parabola, right? No, we are replacing with a straight line. That's the linearization, what it is. So then the simplest the dependence always, if you have two things, one depend on the other, and the dependence is linear. So then how would the force depend on the velocity? What? Nothing but the coefficient. Nothing but the coefficient. It is actually linear means proportional. And then that makes sense because so when the velocity is zero, there is no air resistance. High velocity, you twice velocity, twice air resistance. Makes sense. So at least at the very simplest one. So that's how I would write F is equal to KV, K is the proportionality coefficient. What can you say about K? It is determined by things such as the shape of the object is determined by the medium. Water is one thing, air is another thing. Depends on the kind of air it is. But what else can you say about K for sure?
It's constant.
It is constant. Okay, K constant. What else? That's the proportionality. And what else? The opposite direction, meaning negative, right? Okay, so so the air resistance pushes in the direction opposite of the velocity. So let's make a simpler equation, so we can actually make a progress here. F is equal to negative v. Okay, so that would be the simplest way for a model, and that's my model. Okay, now can we produce a differential equation now from this? Well, the acceleration. So this could be acceleration. This is the velocity. So we can rewrite it as, well, maybe I'll put it here. So I could speak in terms of the position. I can speak of the position. So A, D, E, as we have done before. But as you can see, the force does not depend on the position. It depends on the velocity. So why bring in the position if it's not a part of the equation? So I will simply write v prime is equal to negative v. That would be my differential equation. The acceleration, which is proportional to the force. So why not just to take the derivative, acceleration is derivative of velocity, and then turns out, according to our model, it is actually negative velocity with possible coefficients there, but that's really does not affect a lot. The big picture. Okay, so does it make sense? Derivative of the velocity, which is the acceleration, is the opposite of point in the opposite direction with numbers or with vectors in of the velocity in the opposite direction. Make sense? Well, you can actually guess it from the beginning, probably. You could try to guess what the dynamic looks like before you get to the differential equation. If you have some insight into this, you can guess what the dynamics would be. If not, you go and solve the differential equation. So anybody can guess what the dynamics would be under these circumstances. There are no other forces. So it's not a falling object with air resistance. It's entirely nothing but air resistance. What kind of dynamics do you expect to have?
What was the question? I'm confused.
So this is the model or the phenomenon that we're trying to model. We do have a differential equation already, but let's appreciate the differential equation if we are just trying to use our common sense and try to figure out what dynamics would look like without doing differential equations. Can we envision what it would look like? An object moving through air with no other forces, what would be happening? Forward and there's the resistance. What's the
Slowing down.
It's slowing down. Okay, slow down. Anything else?
Also be falling slower.
Well, it's not falling, but no, it's just no, it is slowing down. But the question and that doesn't resolve the whole thing. Does it slow down entirely to somewhat and then stops, or goes all the way to zero? That would be crucial question, right? So whether or not, in fact, if there is remember the terminal velocity that we discussed, when there is a gravity force, then the air resistance produces what terminal velocity. So it does not stop, right? It will just reaches the velocity and then continues on with that velocity as if there is no resistance. That we're kind of a balance of the force and the velocity. So we cannot answer that question for sure from what we know. But will it slow down? How much? How fast? In what manner? Even if you know it's slowing down like this, will it reach zero or not? And if it does, then how fast? So the differential equation, fortunately, is familiar and not very hard to solve. So how do we solve? What is V? Look at it, the derivative of the function is equal to negative of the function.
Negative D.
Negative what?
D.
What's D? No, this is all, well, if you're speaking of the positional location, then we're trying to actually avoid using it just yet because the differential equation is entirely with respect to the velocity. Only the velocity appears and what is not visible here, but that's the t time. So velocity depends on time, that's all there is. So you need to find v as a function of t. So once again, we differentiate with respect to t and we end up with negative v. What kind of function is that?
E to the negative t.
E to the negative t, correct. So c, actually c e negative t, indeed. That negative in the coefficient of t, that's what produces negative in front of it. Okay, so ask yourself what this function looks like. What does it look like? E negative t, what does it do to the graph? What does the graph look like? It is e means what? Exponential. So there is an exponential growth, and then what else there is?
Exponential decay.
Exponential decay, and this behavior with the horizontal asymptote towards zero. We had this model, it appears. Cooling, heating. Okay, what else? Compounded interest. radioactive decay. This is a very popular model, and then we discovered that that's how velocity will be decaying exponentially. That's what we're saying here, which is all good. But then what we would have to establish also is the so that describes, that tells us that the velocity will decrease to zero, but will never hit zero. But will be approaching 0, 0. In other words, can you, if we were to describe the actual motion in contrast to what I just had over there, so I had this, okay, and now, so we start this, and then what happens? So we start moving, and then initially the velocity is this, and then it will start to slow down in an exponential manner. Okay, so in other words, if this is what happened during the first second, during the second second, it will be, say, half of it. And during the next second is half of it. And then during the next second is half of it. Okay? What's the effect of this? That's the position. Say. So this is the next step would be to find the position. And before we do algebra, let's just, or calculus rather, let's just realize what the question is. What is the question? I plotted it. What's the actual question here? Question is, if there's a wall, will I hit that wall or not?
Eventually.
Well, that's the question. So will I hit the wall? So it is slowing down, and every time it covers shorter and shorter distance. But will it hit the wall? So any other guesses?
Yeah, no,
What?
no.
So we have yes and no. How can you tell?
The series from.
It is a series from calculus 2. That's right. 1, 1/2, 1/4. It is exponential decay or geometric decay. And this one is, the sum is what? It's finite. Okay, so it will, if the wall is far enough, it will never reach it. Because there's an end to it, there's a limit. There's a sum of this series, and therefore what we expect to have here is a convergence of some kind. So we're slowing down, but not slowing down. It's here, just you remember this one, 1, 1/2, 1/3, 1/4. Remember this one? And this one is infinite. So hypothetically, if the model was different, we would end up with a motion, even though it's slowing down faster and faster. Nonetheless, it will follow through and go to infinity. Okay, this one will not go to infinity. It will actually stop it. There is a bound beyond which it will not go, because the sum of this number will be finite. So that's the difference between the two models, which you cannot tell without actually solving it. Now we have, and we can confirm that if we just we integrate. So that was like kind of a qualitative analysis on the left. So if we now integrate this function over here, so P is integral of V dt, which is CE negative T dt. What's the integral? Factor C out.
The negative E2.
Negative CE negative T and
Oh, minus. Over.
plus constant. So I don't want to call it T because it's taken, so okay. So as you can see, that definitely indicates that the graph of my position this time, not the velocity, will look pretty much the same. It will look like this. Okay, so if this is my K, it will be going towards it, never crossing. So it's going down, say, if we are moving in that particular direction, but then it will never pass a certain threshold. Okay, so that's the kind of motion that you have in that situation. As you can see, that's an interesting model. Okay, so it is actually works out pretty well in multidimensional situation. all of that works out in multidimensional situation because we can just differentiate this parameter curve once or twice. The only thing that we have extra here is that, and it worked, but it only worked out because there is no position in our model. So there's no gravity. There is no, even though we could throw in gravity, probably not no trouble really. If we wanted to, we could add negative g, say. Okay, so in a particular direction there might be force. But other than that, what we utilize the fact that because there is no position present in our differential equation, we solve the equation with respect to the velocity, and then when we had the velocity, the second stage of this two-step procedure was nothing but just integration. So a differential equation, that the first step was this one, was the hardest, right? So that's kind of you can say it lies outside of calculus 1. And because it is a regular autonomous differential equation, and we just knew the answer, fortunately, because it's actually separation of variables as well. And then we integrated one more time to get, once velocity is known as a function of time, what we need to for the next step is nothing but the integration with respect to t. And so then the full model is there. So it moves us still along the straight line. There is no other. The force goes along the velocity, which means that the pushing to the side, which means that it will never turn. Okay, so that's what we might discover from this, is that the air resistance is aligned with the velocity, which means that it will never be pushed off the path. Okay, so in other words, it will be every time it will be still moving along a straight line. Okay, so if you start going that way, you will continue going that way. What could turn it, incidentally? What once again, there is no force. What can turn an object in the air? What kind of phenomenon?
Gravitational pull.
Well, gravitation, if you're going towards the Earth, it will not turn. And let's suppose there is no gravity. Suppose there are object with gravity with no other forces, but maybe air resistance, and which is a variation of air resistance, is how about it could be one, could be shape of the object. Okay, so it can push it, that like aerodynamics pushes the object in the direction of depending on the shape of the object. Another one, a simple one, that's everybody has seen it, spin. Right, so if it goes with a spin, then that spin will turn will curve the ball in the opposite direction. So that's all of that requires vectors, obviously. So all right, so as I said, these mostly as far as differential equations are concerned, the vectors will be modeling velocities for the time being, but nonetheless, if you need to understand vectors themselves, also bring in forces, because sometimes they are very productive in that respect. So we got some ideas about how to get started. We started with the displacements rather than velocities. So which means simply that we do not divide by delta t yet, but nonetheless we have made quite a lot of progress because now we can move, and the motion is described by that. So point P plus a vector PQ gives you the next location of P. If you solve it for PQ, then you start to understand the meaning of a vector. PQ is just the difference of 2 points, the endpoints minus the initial point. That produces the algebra that we want to have. That works out perfectly well in a space of any dimension. It's called a fine space, but nonetheless, to understand the algebra of this, where the algebra comes from, well, this is where it comes from. It actually comes from dimension 1, which, as you can see, nothing but algebra of numbers. That's what the vectors are, except they usually originate at the origin. So it's slightly more complicated, but nonetheless, the idea is really when you add two vectors, in this case, two displacements in a row, right? So they have to be aligned head to toe, right? From P to Q, the second vector has got to be from Q to R, otherwise you are not able to add them together. Okay, so if you align them, if they happen to be matching that way, you align Q with Q, and then wherever the endpoint is, so in this case it's R, then that is then you have the sum. So PQ, QR, PQ plus QR gives you PPR. Okay, the direction doesn't matter. The second row shows you the same exact computation, except the second vector goes in the opposite direction. That makes no difference. You still the endpoint, the beginning of the first, endpoint of the second gives you the result of the vector. And that language that I just used to describe, tail of the first to the head to the state of the first, also, and then head of the second, tail of the first. Okay, so that creates the new vector. That language applies to any O dimensions. Okay, so in dimension 2, as you can see, that's the same story. You can have as many vectors as you like, as long as the algebra is not as universal as with numbers. Any two numbers can be added. Okay, with vectors like this, we cannot do that because unless they are head to toe, you cannot add them together. Okay, so it just doesn't make any sense. But if they are aligned, then it is the algebra is very straightforward. Just the beginning of the first and the ending of the last, and you have your sum. That red vector on the right is the sum of those two. Okay, so that's how you can look at the points. Okay, so naturally this all can be interpreted in terms of points: PQ, R, S, and T. Okay, so you can certainly do that. But if you were to look at the vectors, you can sort of look at these vectors added together apart from. So this is PQ and this is QR, RS, and ST, and so these four vectors can actually be factored out and added together apart from the point. And so since they are aligned, Q's, R's, S's, so the end result is PS. So PT. So this one is over here. It is PT. Yes, PT. The beginning of the first, P. The ending of the fourth, which is P. So the vector is P. So it's just nothing but the addition of these pairs, and those pairs are nothing but really just their pairs, literally ordered pairs. So it's not multiplication or anything like that. So you can keep that in mind. So sometimes you see this, by the way. You must have seen this, right? So putting an arrow on top of these, it is normal occurrence in many sources. It takes time to. It takes more time. It's more cumbersome, and it takes time to typeset, and so that usually can be ignored if the context is clear. And then you have cancellations here. So then another way to see it, if you think of these vectors as differences of locations, such as, once again, PQ is equal to Q minus P, PQ is equal to Q minus P, then when you start adding those vectors, there is the cancellation of the points that they share. Okay, so PQ plus PQ plus QR is actually Q minus P plus R minus Q, and then, as you can see, Q cancels out. Q cancels out, and then you can continue on in that fashion. So the algebra and the geometry, they fit together. Okay, so that's the algebra, and so now we understand addition of vectors, more or less, to begin with, without using coordinates just yet. Because this is all can be drawn on a piece of paper. You can even imagine that you have a three-dimensional space and you can still do these. And you can imagine how you can connect to head to toe, no problem. If you can imagine multi-dimensional spaces beyond dimension 3, you can also do the exactly same idea to be implemented. That's not a problem. Okay, so let's understand algebra a little bit better, considering that we are using entities that are entirely new, and we're treating them as if they were numbers. Okay, so we're using this plus sign, we're using minus sign, we use the equal sign. So surely we have to be very clear about those symbols. So this is how you can interpret algebra vectors without invoking forces. So the forces, this is how we use forces. Okay, so that's what as far as in our context, this doesn't quite work. Not ODEs not ODEs of the first order. Okay, so if you want to do forces, you have to go with second order. So these are second order P double prime, second order. Okay, so we're not doing them. We haven't been doing them at all. okay? With the exception of what we just did a minute ago. So that's why a better is this, and you can explain it still effectively if you just look at the velocities, but a little bit take some thinking, because here there's a flow. The blue arrow indicates the flow of of water in this canal, and then the second one is your effort as a rowing. Okay, so you are aiming across the canal, that's the red arrow, and then the flow is going in the along the canal. So the end result is, as you can guess, will be something in the middle. So you're gradually crossing the canal, but at the same time you're drifting quite literally. Okay, so if you want to have a net effect, that's how you do it. You take these two vectors and add them, and you can see how on the right you can see what adding these two vectors means. So let's add them. If you are not clear what it means to add two vectors, that's what. Okay, so literally you see how progress you have made in the horizontal direction, how much progress you made in the vertical direction, and then you add them together. So in that sense, maybe it is actually better to thinking not in terms of the velocities, but rather displacements. So literally you are looking at if you are rowing across. So then you can actually ignore the draft, and so you just seeing how much you are progressing across the canal, and that is how depends entirely on how hard you are rowing. Okay, and then so that's you're observing one dimension, and then separately, or maybe another person observing the direction, what's happening to your motion along the canal. It's once again like you have two observers. Remember, we did that with parametric curves a little bit, right? So two observers. This is the rower. Okay, this one somebody's on the or just somebody on the boat. And if you're rowing, you're looking like this, and you're seeing how fast you're progressing in the how closer the shore is, and this person is on the shore, and that person only sees the drift. Okay, so then if you were to combine the information, then you would have to carry out this algebra here. Okay. So once again, it is, as you can see, the motion is two-dimensional, but it can be split into two dimensions separately. That's if you go the same thing in reverse. That's the addition of the two vectors. That is the addition in the form of a rectangle. Even though it is not as much as about a rectangle as about a parallelogram. Why so? Because you could be rowing not exactly perpendicular to the flow. You could go with the flow or against the flow, so the relation between the two does not have to be necessarily perpendicular. But then the idea is still the same. Then you add them together in this way. So it's called parallelogram addition. If you haven't seen that before, so that's what we're thinking. So once again, if you look at the displacement, that's how you explain this addition. You are so you can, as if you have two ways to go two ways to take this trip. So you take a free flow trip 3 miles north, okay, followed by walk 2 miles east over a bridge, okay. So you are that's the two distances that you have to cover, or you move across the bridge first, and then you go along the river, or you can go diagonally if your velocity is exactly that, 2 versus 3. Okay, 2 in this direction and 3 in the north direction. Then that's the effect will be the same. So the number 1, number 2 trips are pretty much walking, and number 3 is your boat. Okay. So so we have two ways already we discovered to add vectors. Head to tail, forms a triangle, or tail with tail. That's a parallelogram. Actually, they produce the same result if you compare them to. So it's the same red, the same green. Okay, so the difference is where they are aligned. So if we were to speak of forces, especially like with those springs, like these springs, they're affecting that ball in the middle, and naturally they push it, pulling in the opposite directions, but they apply to the same point. If you speak of displacements, then they have to go head to toe. You move from A to B and then from B to C. Okay, doesn't matter if we think of a vector as just a directed segment. Then we can move them around, and then from that head to toe, we can move it down and align them all to at the toes, and then we can carry out the addition of head to toe construction, or completing the triangle, okay, or we're completing parallelogram in the bottom row, and as you can see, it's that half of my parallelogram is my triangle. Okay. So that diagonal is the triangle over there. So it's the same thing. They're just aligned differently. So then that certainly justifies. That's a reason why we actually don't want to do both of them, but rather not do them separately, but rather do them together. And all we have to do is to concentrate on vectors that originate at the same point. Okay, so rather than doing some copying and stuff like that, we will still have to do copying, but we have to sort of have in mind both of these operations as if they represent the same thing, and they do, right? So once again, let me point it out. So this vector and that vector are the same. So same. Okay, so same in what sense are they the same? They are not located in the same place necessarily, but surely they can move in one into the other because they have exactly the same direction, exactly the same size. Okay, so that's once again the addition. We already looked into that. The naming of the vectors is sooner or later we'll have to do this. And name vectors as by single letters rather than by two letters that represent beginning and the end. So we sort of abandoning that approach and just think once again a vector A, vector B, vector C, whatever. Just like with numbers, they deserve one single letter per vector. So it doesn't matter where it starts, where it ends. It is that information is hidden. Okay, so once again, this is the addition. So that's the thing about vectors, what they give us in comparison to geometry. Geometry on the left, a new vector algebra on the right. You can see, so all triangles become addition diagrams, right? So a triangle PQR will actually it is a vector PQ plus QR gives me a vector PR. Okay, so that's really what the advantage is. Naturally, what extra thing that we get here, and that's not obvious, is there is more here than on the left because the triangle may be degenerate. Okay, so it is possible. What if Q is located here? Then there is no triangle. But there is no trouble whatsoever if we carry out this operation with with vectors. There is no trouble. So this is A, this is B, and this is B, and this is A plus B. Okay, so there is no relation so it does have to be a triangle in order for addition of vectors to make sense. Okay, so that certainly is convenient, and then we'll see more things that we can use. All trigonometry comes into play in a more kind of advanced way. So not necessarily triangles. So we don't have triangles anymore, which is the good news. And we can do a Cartesian system as well. So these vectors now will be expressed as in terms of their directions and magnitudes as part of the Cartesian coordinate system. Okay, so you can pretty much see them once you start plotting these vectors on a piece of paper with a grid. You start noticing things. You notice that every vector is ultimately has the direction and has magnitude. But before we do that, their subtraction of vectors makes perfect sense too. So if you understand subtraction is just the inverse of addition, then what's the meaning of A minus B right at the top? It's simply such a vector C that when added to B produces A. Okay, so I have two vectors like this. How do I subtract them? Well, I need to find a vector that when I add it to B, I get an A. And so that's the blue vector answering the question, right? So we'll look at the diagram on the right. It is green is B, blue is C, B plus C gives me A. Okay, so that's, there is nothing special about subtraction, just the inverse of addition. And so as you can see, it works out. Just as something to maybe remember, the triangle addition corresponds to triangle subtraction, except this is the slightly trickier part, is that vector has to be moved. If it was especially about forces, that vector that we just found would have to be placed at the starting at the origin, which is what we are ultimately after, rather than thinking about head to toe vectors going into in a different paths that we take, but rather they all start at the origin and they are moved wherever we want, whenever we want. But ultimately, all the vectors originate at the origin. Okay, so they look like this, and once that is the case, we can simply think in terms of the coordinates of the endpoints. Okay, so we'll get to that later, but before I don't want to do it too early. Okay, so let's look at the vectors just as arrows and see, and with algebra that we know, and see what algebra we can do. We can do addition, subtraction. What else do we have? There's a zero vector, by the way. Remember, a zero vector, which when the displacement is trivial, non-existent. What this is the zero vector. You can think of it as if it is the velocity is zero. You can think displacement is zero. You can think of force is zero. Okay, so but ultimately it is a point that the arrow with no length. Okay, so which means that, by the way, it doesn't have any direction. Okay, so you have some kind of length. You have to have a length in order to have a direction. Okay, so then as you can see, look at this equation. Once you start adding vectors, some interesting things start to happen. So p plus 0 is p, where p being a vector, right? Then it looks like you're doing numbers, right? So that's zero vector, by the way. So let's be clear that this is not a number. It's written as a number, but that's the thing we have to pay of ambiguity, is that we're using the same letters, the same algebraic notation, plus sign, minus sign, equal sign, and now zero symbol in order to describe things that are not numbers. So that seems like something that we don't want to you don't want to do. It seems like unnatural, but it's not. It's not. And to begin with, they behave like numbers, or at least to a certain degree. And secondly, it's not entirely, you haven't seen this. So you might remember first, second, third grade, and you start doing algebra of integers, right? 1 plus 2 is equal to 3. But then you go from integers, you go to fractions, right? Rational numbers. And then it turns out that the fraction are subject to the same rules. Okay? So you can add, subtract, multiply, divide them, and so it's seemingly you were doing the same thing, but with something entirely different. And so you're using the same notation, and then you go from rational numbers. Where do you go? From rational numbers, where do you go?
Irrational?
Oh, yes, but you add irrational to rational altogether, they produce the real numbers, right? So you expand. You don't want to switch from rational to irrational, because when you subtract two irrational numbers, you might produce rational number. And so irrational numbers as such, they don't really exist as kind of a base of algebra, because what we want to do, when you add two rational numbers, you have a rational number. Okay, so it's just like with integers. So that's what you notice early on. The algebra of integers, unless you do division, algebra of integers is self-contained. Okay. The algebra of rational numbers is self-contained, and so the algebra of real numbers is self-contained. And then we're going to do the algebra of complex numbers. It's also self-contained, and then we're using the same symbols everywhere. And so it's not at all unusual to use, once again, the same set of symbols for algebra for vectors. Okay, so and these are two-dimensional vectors, so it's at least we can visualize. Okay. Okay, so here there is a scalar multiplication. So one algebraic operation on the vectors to addition and subtraction on the flip side. But what we do not multiply vectors by themselves. You don't multiply one vector by another vector. but you do multiply a vector by a number. Okay, so very easy idea, right? So especially in dimension 2, dimension 1 rather, you take that vector, which is a directed segment, and just make it twice length, thrice length, and that's what it is. Think about forces. That is you triple the force, and so its vector triples. If you have one person pushing that object, then you have three identical people pushing in the same direction, then the force triples. So that's the idea behind it. With velocity, maybe not as obvious, but certainly if you're looking at the speedometer, then yeah, you're driving 20 and then you drive 60. You know that you have tripled your speed, and therefore you have tripled your velocity too, right? Velocity meaning that the direction also matters. So it is change, a proportional change, okay, and this is what is done to them, to vector A, 2A, -A points in the opposite direction. Half A is half the length, and you can even multiply vector by 0 with producing the 0 vector, which is the on the right. Okay, so once again, be careful there. That's the new thing about if you haven't seen a lot of vector algebra, that's a new thing, because we are developing algebra, but it mimics a lot the algebra of real numbers, but with certain exception, that's the one. We actually multiply two different entities by each other. So a vector is multiplied by a number. Okay, so not by another vector. So scalar product, that's what it's called. Scalar refers to a number as opposed to a vector. We're using the same symbol. Naturally, when that number is positive, then the vector points still in the same direction. When that coefficient is negative, we are pointing in the negative direction. So that's could represent the velocity, the velocity of the wind. Okay, how we can have different directions in dimension 2. That's how have a bunch of that's what a wind map would look like in a weather forecast. So how do we go to high dimensions? That's how. So just the prediction of if you were to do differential equations or linear algebra in higher dimensions, there is not much of extra work to be done, because the operations are defined for one vector at a time. So it doesn't matter where vector lies. So vector lies on the plane like this, or it lies like this in three-dimensional space. Okay, so how do I double? There is no trouble whatsoever. I still can double it. It just happens to be as if it is drawn on a piece of paper. I just expand it by 2, and that's how you double a vector. Adding vectors, addition diagram of vectors is nothing but a drawing on a piece of paper. So that piece of paper might be horizontal if you're doing two-dimensional stuff, or it might be like this. So if you have two vectors like this, how do I add them? Well, I make sure that they lie in the plane. Two vectors always define a plane, and which means that we can always carry out this operation here as if we are living still in the two-dimensional space. So that's why we speak of Euclidean spaces, because they entirely take all the geometry and algebra from the Euclidean space, which is the one of the plane Euclidean. Okay. So let's skip this. Subtractions, axioms. So that's less. It's quite profound, and so I'm not sure how much we're gonna use it, but it's always good to whatever things that we have established, write them up. When we do, we write them up and call it a theorem. So in this case, we even call them axioms. Axioms of a vector space. So they're vectors, and there are points in that space, and then points are added to vectors, as well as vectors are added to vectors. Okay, so there's a 0 vector that added to any point gives you the same point, or you can do there's also the algebra, that the properties that you might know from algebra of numbers. So for example, associativity of addition. So p plus v and then plus w, or p plus v plus w gives you the same effect. Once again, the operations, addition. This is addition in 3D. Okay, so it's the same. We're not going to do it 3D, but nonetheless, it's well worth mentioning here. Okay, so this is, if we move all the vectors to the origin, that's what they look like. Okay, so we ignore, whenever we need, we take that any of these vectors, we can translate it into elsewhere. But otherwise, this is what we're dealing with. All the possible vectors, they actually originate at the origin. They start at the origin, so pointing in all directions with different lengths. So these are the operations. Vector plus vector is a vector. Number times a vector is a vector. So that's why we speak of it as a space of vectors, even though it includes indirectly the algebra of numbers. Okay, so because the scalar multiplication includes multiplication of numbers. So let's look at coordinates. So now once Euclidean space has been fixed, so it's as if we had we were doing this stuff on a piece of paper, drawing, and then we took a piece of plastic with this grid on it and placed on top of it, and then all of a sudden, every vector is actually associated with two numbers. Okay, so and if we take a look at it, then the red one is, as you can see, is 2. 1, 2, and I'm using once again these triangular parentheses for vectors as opposed to circular ones that for points. This is 1, 2, and this is 2, -1, right? Look at the coordinate of the endpoint of our vector. That is the component representation of our vector. Okay, so then if I were to add them, that might not be entirely obvious from the picture, but once you plot it, you can see the, especially if you right here, this is you're doing addition separately with respect to x and with respect to y. So 1 is combined with 2, 1 and 2, so it produces 3, 1, 2, and the n is 3. Okay, so that's your addition. And then you take the other coordinate, and this is 2 and -1, and then I have 2 and then -1, or let me put it here, 2 right here, and this is -1, and so altogether I end up with this, which is 1. Okay, so then indeed 1, 2 plus 2 -1 gives me, which is, you can see here, the blue one, it is 3, 1. Okay, so it matches our geometry of the triangle construction, parallelogram construction, and then but coordinate wise addition is really simple, because as if the two components, two directions exist separately, and then you just do addition separately entirely. So it is actually simpler than, well, might give the impression that it is really simple. It is simple, but not as what one might think. Same thing happens with scalar multiplication. You do it coordinate wise. So if this was 2, 1, and you multiply by 2, component wise, once again, 2 times 2 is 4, and 4, 2 is your vector. Okay, so once again, my algebraic operations on vectors are very simple. They're both component wise. And well, that's all there is. And you can imagine that in dimension 3, there will be 3 numbers. In dimension 4, you have 4 numbers. It's the same, pretty much the same story. Okay, so that is the algebra of so points and vectors. Okay. So we did algebra with vectors, but we also did geometry with points, and meaning that specifically distances. And if you remember trigonometry, that is distances, angles too. Okay, so let's take a look at that, and then I try to link them up. How can we have geometry of vectors in addition to algebra of vectors? So this is algebra of vectors. Well, is there geometry? Yes, there is. Yes, there is. Certainly, we can tell the length of a vector, right? By if we have geometry lined up, we can do algebra of vector. We can do geometry of vectors as well. Okay, so that's what it is. This is a geometry just in dimension 1. Okay, so if you were to find the distance between point P and Q, what do? You subtract. in this case, one is 2, the other one is 7. Whether you're going from 2 to 7 or from 7 to 2, it doesn't matter. The distance is 5 units. Okay, so that is the displacement, if you like, but well, it's not the displacement. Why so? Because and you can see there is no arrow because we're ignoring direction. Okay, so if we were to ignore the direction, why would we want to ignore the direction? So it is an important concept is the speed, right? So every vector is described by two things. Its direction and its magnitude. So then in that sense, we have to be that's what the speed is. It is the magnitude of the velocity. Okay, so in dimension 1, it is you can tell. So remember what P and Q. What's the operation? The distance between P and Q. P and Q are numbers. What's the how do we find distance? How do we find the distance between two numbers?
And the absolute value of two things about
Absolute value of what?
two things.
Well, the difference. The absolute value of the difference. So literally P and Q are numbers, so either 7 minus 5, 7 minus 2, or 2 minus 7 doesn't matter, because when you take the absolute value, the end result is 5 either way. Okay, so that is the idea, is quite productive once you understand that about numbers. We'll do the same with vectors in higher dimensions. So we will be subtracting them, okay, and then looking at the magnitude of the resulting vector. So that's the insight that we're gonna carry on to the 2-dimension that what we really care about. Subtraction and the magnitude, that's what we see. Subtract, and then I take magnitude. Okay, so all right, so let's do that. So once again, this is just a shift. Okay, so if you were to do the magnitude, that's you could shift it to the origin in order to facilitate that computation. Okay, so the change from P to Q, we look separately from the change with respect to X and with respect to Y, and then we subtract them, and that's what happened when you move the vector to the origin is P disappears, it becomes the 0, okay, and then rather than thinking about the coordinate of P and coordinate of Q, 4 numbers, we're looking only at 2 numbers, okay, so it's a big simplification. So once again, from this to that, and then indeed that's that I'm writing the vector with a triangular parentheses brackets, and so in this case, so we're going 1 point is 1 1 1 1 1, right? So this is 1 1, and this is 2 5. Okay, so I don't care about where they are, I only care about the change, which means that I'm looking at the change with respect to X separately, which is 1, with respect to Y separately, which is present for it. Okay, I think this is a typo here, so it is actually 1. This is 1, and so this is 4, and this is 1. Okay. So the changes only we care about, and unfortunately, once again, the change with respect to different directions are related to each other. We subtract, and that's the vector that actually we care about. The green one has components. We don't speak of coordinates. And 1 4. Change horizontally 1, vertically 4. Okay, so that's pretty much how if you want to write up how components of the beginning and the end of the points of P and Q are taken, their coordinates are found, and then you just subtract. So the end point is Q, subtract minus the beginning of the point, and then you have the 2 numbers, and they're called the components. Okay, so that's literally what it looks like. Once again, I don't want it be vectors to be confused with the with points, and so I'm using the brackets, different kind of brackets. Okay, even though they're, just above and it. This is a very important innovation also. Instead of going horizontally, we're going vertically. It seems like entirely trivial point of view, but it will be proven very effective. So a column, a vector is a column. It's not a row. It's not a row. It's not a string. And so we align them in the vertical direction. And so it could be as long as we like. Okay, so we'll see how that works out very nicely in when we get to stuff that is more more down. Okay, so then once the vectors components are established, the algebra is executed component wise. Then once that is established, you can do addition of vectors very easily. Really, it is algebra. Literally, it's there is nothing, no advanced operations to worry about. So I have these three vectors: blue, red, and green. How do I add them together? You can take a look at it. That's done with Excel, by the way. So so as you can see, vector A has components 3, 0, the red one. B is 0, -3, 0, -3, and the blue one is C, which is -2, -2, -2, 2. Okay, so naturally, component wise, once again, it's you do more with Excel than with anything else here. So 3 + 0 + -2 gives me 1. I'm going look at it. I'm going horizontally, right? So I'm going like this. So 3 zeros. 3, 0, 3, 0, -2, and the result is 1. Okay, so if I go on the first row, on the second row, I have 0, -3 + 2, that gives me -1. And so my vector is D with components 1, -1, and that's, as you can see, it's slotted automatically as the purple one. Okay. Once you write this little spreadsheet, you can move the vectors around and change them entirely as I did, and the end result will be the same. So for example, here, not the same, but rather the point is that it is so automatic that no challenge whatsoever. So that's addition of vectors, how we can execute them with Excel, no trouble. So so once again, this is what I just said. Components of a vector are simply the coordinates of its end. So a vector, as we from now on will be concentrating on, are the ones with the origin at the origin. So the starting point of a vector will be O, the origin, therefore only two numbers for us to worry about, and then that's the coordinates of the endpoints will be x1, x2, and so x1, x2 are the components of our vectors. Okay, so the execution, look at it. This is addition. You can do them horizontally, very nicely aligned, and once again, align x's with x's, y's with y's, carry them out separately, and that's the result. Or you do them with the column notation on the right, and then you go horizontally at x plus u, y plus v. These are the components of the new vector. Okay, if you go to n-dimensional case, what the difference now? Not much difference. Once again, you're doing them, do them in the second. There's a typo here. Right. So this is okay. This is a typo here. Okay, that makes sense. Okay, so as you can see, the what's in the box here is simply the addition, that is the vectors do not have to be called and expressed in terms of the points anymore, but you can entirely concentrate on the vectors, and that's what happens on the right. Scalar multiplication is next. Okay, so once again, component wise, every component multiplied by that number by the same proportion. If you multiply by different numbers, the vector will rotate. Okay, so if you multiply them by the same number, then it will elongate or shrunk by the same proportion. Therefore, the direction remains the same. It is, if you care, you can ask yourself why it is the case. So not too hard to see why it is the case. So, well, so if I take a vector and this is, say, x, and this is y, okay, and then I go with here, this is 2x, so this is 2y, and then so you can ask yourself, okay, so then you can see what I did here. I took a vector and multiplied by 2 by multiplying both components by the same number 2. Okay, so the picture itself, whether it gives it credit or not, the question is, and that's a question to ask, why are they parallel? Why are they parallel? You can make a case, with a reference to, I suppose, high school geometry. Or not necessarily geometry, or maybe something else, or maybe Cartesian system. So why are these two vectors or lines, why are they parallel?
The same slope.
The same slope, right? Exactly. That's the way to do it. So slope in either case is y over x, or it is also is equal to y over 2x, which happens to be the same, right? So yeah, same slope. So that's the answer right here. And so, yeah, so that's what we know from the Cartesian system, is that lines with the same slope are parallel. Okay, they're in the sense that they never intersect. Okay, so constant multiple, remember calculus, constant multiple rule, you have sum rule, you have constant multiple rule. And so if you were to actually study linear algebra some more, you will notice how many things in calculus are entirely about that. Okay, so once again, addition of vectors, component-wise, scalar product component-wise. So just for the record, if we were to introduce algebra of vectors, and then it is done coordinate-wise. So naturally, the geometry that we still keep in mind, but it is probably better place to actually not to start, but rather to work to use to do computations is here, rather than with geometry, which geometry does not translate into high dimensions anyway. But if you get used to doing algebra component-wise, there you go. You have the algebra of numbers. Sorry, the algebra of vectors in any dimension. So this is just a two-dimensional case. Okay, so once again, this is a three-dimensional. There is no difference. Once you get the idea, there is no challenge whatsoever. It's just adding component-wise. You have 3 and 3, so you component-wise add them together, or you multiply by a constant. So the algebra, what the point here is the algebra. Does the algebra of vectors match the algebra of numbers? And here it is. You can see the point. We call it commutativity. A plus B is equal to B plus A. Okay. So that's what we know about the numbers without actually thinking about it. But it turns out vectors is also true for the vectors. You can certainly prove it by doing the geometry. Okay, so there is a zero vector with the one with 0 components. Then you have the negative vector, which is simply flip. How do you flip the vector in the opposite direction? You flip both the components. Okay, so yeah, so we flip. Okay, the decomposition is a crucial step as well. Okay, so if you have a vector, and then as you can see, there is an origin and nothing else. So you have a vector starting at the origin and just drawing an arrow. If you bring in the Cartesian system, place that plastic on top of it, then you need to find the vector in the numerically represented, which means that you need the components. And so how do you do it? You are adding, as I said, you add axes, and so then you just concentrate on the endpoint and you find the coordinates on the endpoint, right? That's all there is really. And so as you can see, the component of the first one is 3, of the second one is 2. So then you can say that the coordinates are 3, 2, but also, and that's also I want to emphasize is this, that actually it is the sum of 2 vectors. It is one vector, horizontal one positive, one horizontal, one vertical, and every vector can be represented in that fashion. Okay, so decomposition in two directions, and that not only such a thing exists, it's also always the same thing. You cannot have 2 different decompositions. So that's once again. So that's what decomposition means. And you can even take it further and decompose them into what we call a linear combination of vectors, but specific horizontal and specific vertical vectors. They call the basis vectors 0, 1, and 1, 0. And as you can see, the 0, 1, 0, red one, the green one is 0, 1. And then as you can see, my vector 3, 2 is, look at it, how I'm using linear algebra here, is 3 times this vector plus 2 times that vector gives me the vector. Okay, so I'll stop here and I'll just let you go. Thank you. See you next time.